Hi everyone, I'm Edu from PSC at the EF, and today I will talk about I will talk about a review of the different RISC-V zkVMs and others, not just RISC-V. So a quick overview, I will give a brief introduction to RISC-V, then explain what is a zkVM, then do an overview comparison of some of the different zkVMs projects that we can see, and then explain some points of the architecture of how they are designed, and finally present some benchmark results. So first of all, about RISC-V. RISC-V is an open architecture that follows the reduced instruction set paradigm, which means that there are not many instructions and the instructions are usually simple. And in particular, it has two variants, one for 32 bits and the other for 64 bits, where the 64 ones is an extension of the 32-bit version. And then there is a base instruction set with some bitwise operation, arithmetic operations, and all the necessary instructions to jump around and read and write memory. And then there are some extra extensions defined by the standard, like for instance, multiplication and division are not part of the based extension. There's also atomic, compressions, and so on. And why is RISC-V interesting in this sense? Well, it has major support from the popular compilers like GCC, LLVMs, you get Rust, you get the Clang compiler, there's also Golang, and many other languages currently target RISC-V. And now, what is a zkVM? So in this sense, the term VM is usually used for software machines, but in this case, we're also using for hardware machines. So basically, it's a model of a computer that can do arithmetic operations, can do bitwise operations, can do branching, can access to some memory, and this gives us Turing completeness, so we can execute any kind of program in a VM. And a zkVM is just a system that allows creating proofs of the execution of a program under this VM. So we will have a program, we will run it under the VM, and each instruction of the program will give us a trace. So we have this execution trace. And then the idea is that we will have a circuit that proves that this trace of execution that the VM has followed is correct. So now a quick note on privacy. So we call them zkVMs, and zk stands for zero knowledge. But most of the current zkVM projects are not providing privacy. Probably it's not something hard to realize, and maybe in the future we'll see some zkVMs that add privacy. But for now, just have this in mind. And there is a term that properly describes what we want to achieve, which is the verifiable computing. So here, most of the times, we only want the succinctness part of the snark. Okay. So after this introduction, here is like a big list. There are 11 zkVMs presented in this table. I have to say that this table is not exhaustive, and I probably missed some. And the ones I want to focus are the ones that are targeting real hardware instruction sets. But I also added some to have the full picture. For instance, I added Cairo VM, which is like an old zkVM project that uses on its own instruction set. But the ones I'm focused more are the ones on the top. Yeah. Okay, so first let's take a quick look. So we can see that these four are RISC-0, SP1, and Powder. They are using the RISC-V instruction set. So RV is like how the different extensions are encoded. And in particular, they are all 32 bits. Then we have two projects that are using MIPS. MIPS is another RISC instruction set, and it's also targeting 32 bits. Then we have one which is zkWASM, which is targeting the WebAssembly virtual machine. And then finally we have 4 that have their own zk-friendly instruction sets. So they are instruction set customly made to be verified under zk circuits. Then if we take a look at the arithmetization of each, we can see that quite a few of them are using error arithmetization, and this is usually combined with the star proof system. We also have some Plonkish, it's also quite popular. And there is one that is interesting to mention, which is Jolt, which is quite different in the implementation compared to the others. So Jolt mainly uses the lasso lookup, which is a decomposable lookup that we will see a bit later. But basically it's not, instead of using arithmetic constraints, it's mainly using lookups to prove the instructions. Then if we take a look at zkVM framework, I think it's interesting to see that a lot of these projects are using their own custom libraries to write the circuits, but we still have some that are using Plonky 2 and 3, Halo 2, so it's a mixed bag of existing libraries and custom libraries. Then in terms of proof systems, we see a lot of Starks. So probably the reason we see a lot of Starks is that Starks combined with Fry and small fields gives us very good performance. But we still see some like folding schemes with Nexus zkVM. Then Jolt is like its own proof system with a combination of Spartan and Lasso. And another interesting mention is Powder. Powder is actually not a zkVM, it's a framework to build zkVMs, but they also provide an implementation of RISC-V, and in this framework you can choose the different proof systems. And finally, on the field size, we see that small fields are very popular, but we still have like Baby Bear, Goldilocks, they are all small fields, but we still see some projects that are using big fields with the BN scalar. Okay, so now another way to compare these VMs is trying to categorize them. So Vitalik made a blog post where he proposed some types for zk EVMs, and I thought about trying to do the same exercise but for zk VMs. So in this case, there are some parts of the Vitalik categorization that match on map and others don't. So the first type would be zkVM that follows the instruction set specification of a hardware CPU, and it's following fully, and it includes the decoding of the instruction in the circuit. The second type would be it also follows an existing instruction set of a hardware CPU, but the decoding is not done in the circuit. So the decoding means that the program is in bytes, and there is a step where each byte is converted into the instruction, arguments, and so on. So in type 2, this decoding would be done in a pre-processing step, and then inside the circuit, the instruction would already be decoded. So for instance, this already forbids us from doing just-in-time compilation or ahead-of-time compilation, because we cannot write and execute the memory. Then type 2.5 is very similar to type 2, and probably the jump from 2 to 2.5 is not very meaningful. So in type 2.5, some instructions would be translated or expanded into a list of instructions, some transformations. And the reason why I say this is probably not meaningful is since we already have pre-decoded the instructions, having to do more steps for one RISC-V instruction is not very meaningful, because CPUs already do several cycles per instructions, and some instructions take more cycles. Also, CPU are usually implemented with microarchitecture, which means that internally they are doing several instructions per instruction. And finally, we have type 3 and 4, which would use a custom instruction set that potentially could be zk-friendly. And the difference is that in type 3, this instruction set would be like close enough to existing hardware instruction set that an existing compiler can be used. And in type 4, it's so different that we need a new language. And here we can see like the different projects we saw on the grid before laid out. So we have all this list of RISC-V and RISC-V, WASM, and MIPS zkVMs. They would fall in the category between 2 and 2.5. So for Jolt and RISC-0, I was able to check that they translate some instruction to multiple internal instructions. For these 4, I was not able to figure out, so I just put them in the middle. And then we have Nexus zkVM and Valida, which have their own custom instruction set, but they offer easy ways to translate RISC-V instructions to their own instruction set. You can reuse, for instance, the output of an existing compiler. And finally, CairoVM and TritonVM, they use like completely different instruction sets. And something interesting to mention is that the original categorization by Vitalik had this chart where we have more compatibility and more performance. But the authors of Jolt, which is a RISC-V zkVM, argue that you can get very good performance with a RISC-V zkVM, and you don't need to do a custom instruction set. But I guess time will tell. Okay, now let's take a quick look at how the architecture of these projects are. In fact, I want to mention that this architecture also applies to zkEVMs, which is a special kind of zkVM. So usually we will find 2 main blocks. One is the CPU, which performs a basic loop to fetch, decode, execute, and do memory reads and writes. And also we also need another block for memory to be able to prove that every read to an address has the same value as the previous write to the same address. And then there are extras, like when we have a zkVM, we're running a processor, but there's no operating system, and the operating system usually gives us a lot of features, so we may need a way to have heap memory, standard input and output, threads, and so on. Then there's also a topic of continuations and coprocessors that we will see later. So for a first example, this is how SP1 looks like. So SP1 is a RISC-V zkVM. So all these green blocks are like circuit blocks defined with error constraints. Each one has their own error constraints. And the idea is that they can talk to each other via lookup arguments, and all these lookups are joined into a single lookup argument. So the main entry point in SP1 is the CPU, and then it executes or verifies 1 instruction per row. So in particular, it will fetch the instruction from the program, so it will do a lookup to get the current instruction at the program counter from the program. Then it will prepare the arguments for the instruction. The arguments may require a memory fetch, which is another lookup to memory. Then it will apply the instruction. So basically in the CPU we have a state which is all the registers, and the instructions will tell how these registers need to be updated. And some of these instructions will be implemented in the error constraints of the CPU, but for more complex instructions, they will be implemented in other errors, so they will be verified by lookups. And then the error itself will verify the instruction. So yeah, then the CPU state will be updated, and possibly the result will be written to memory, again, with lookup. Okay, now a different example for architecture is Jolt. So Jolt is very peculiar because it's built with lasso lookups. So in this case, for Jolt, every RISC instruction from the basic instruction set is defined with decomposable lookups. So what is a decomposable lookup? I tried to make like an example diagram here. So the idea is that you take the instruction with the arguments, and the arguments are going to be either 32-bit or 64-bit values coming from the registers or memory. And then these values are chunked into smaller parts, so for instance into 8-bit values. So for instance, we take the first 8 bits of A and the first 8 bits of B. Then we do a lookup to a subtable with these values and get a result. And the same with other chunks. So at the end, we end up with results of lookups to these subtables. And then we have all these results, we combine them again, and we get the final result. And in Joel paper, it explains how to express all the RISC-V instructions in terms of this decomposable lookup. And Joel not only does this, but once it defines the lookup for each instruction, it merges all the subtables and it merges all these expressions to combine to decompose the lookups. So at the end, it's just one single lookup expression, decomposable lookup, for all the instructions. And there's some details. There are some instructions that are hard to do with lookups, so they have some R1CS constraints for those particular instructions. And also, to add glue and update different parts of the state, they also use R1CS instructions. Okay, so now we go to the more general specific features of zkVMs. So one of them is continuations. So in some cases, we may have a long computation that doesn't fit in a single proof, and the reason could be either because the memory requirements grow with the size of the proof, and we reach prohibitive memory requirements, or perhaps the proof system has a limitation. So in this case, the continuation is the idea of splitting the computation, the execution trace into chunks, and then for each chunk we'll have a proof, and we need a strategy, ideally, to aggregate these proofs into a single proof. This split also requires some details, like how do we connect the end state of one chunk with the beginning state of the next chunk, how we connect the memory, how it was left in the end of one chunk to the next chunk, and so on. And this is not supported by all the zkVMs, but actually quite a few support it, and probably the ones that don't support it will implement it in the future. So here is how, as an example, how continuations work in RISC-V. So in RISC-V, the first part that they do is they take the entire execution trace and split it into segments, and each segment has the equal number of cycles or steps. So in this case, they call them cycles, but it's one instruction per cycle, which is not usually the case of CPUs. CPUs usually take many cycles per instruction. Then once we have these segments, we need to find a way to pass memory around the memory state. So in particular, from segment to segment, the memory will be passed via Merkle tree. So this is going to be a Merkle tree where the leaves contain pages of memory, and at the beginning of one segment, there will be opening of the pages that will be the read or write in that segment. Then during that segment, all the memory is going to be verified with the permutation check and sorted table. You can learn more about this here, but this is a common trick to prove the memory correctness of RAM. And then finally, at the end of the segment, all the different pages that were written will be committed back to the Merkle tree. So now we can pass this route to the next segment. And the way that all this is composed is that each segment is proved with a Stark. So this will be all the segments proved. Then all these proofs are aggregated in a tree fashion with more Stark circuits until we finish with one single Stark proof. And this Stark proof can be a bit big to verify on chain. So there is a final step which verifies the Stark proof in a Gross 16 circuit. And then this can be verified on chain. So we have a single proof for unbounded computation. Okay, the other part that is like a feature of some zkVMs is the idea of coprocessors. They are also called precompiles, which matches the nomenclature used in Ethereum. So the point is that some programs, when they are translated to RISC-V instructions, they may take a lot of steps for some particular functions. And sometimes, if we can identify that these parts are a bottleneck, we may try to write specific circuits for this part to accelerate the proof computation. And some examples would be elliptic curve operations, hashing, and probably there are others. And this is supported by less projects, but again, probably at some point, all of them will support this because it's a very interesting concept. And here, as an example, this is how SP1 handles the coprocessors. So on the instruction set level, the coprocessors are accessed via system calls. So that's how the program will access these features. And then on the circuit level, for each coprocessor or precompile, there will be a new air circuit that shares the memory with the CPU. And in particular, this coprocessor air circuit will be also looked up via the joint lookup we saw before. And it's interesting to see that since this coprocessor has access to the memory, you don't need to pass all the data when doing the lookup from the CPU, you can just pass pointers. So this is an example of the SHA-256 compress function, which is a function that just does like one call to SHA-256. So the CPU will do a lookup passing two pointers, which are the word memory, which is the data we want to hash, and the SHA-256 state, which contains the current hashing state. Then it will do a lookup to the SHA-256 compress air, and this coprocessor with air constraints, what it will do is perform the computation, but first it will read all the bytes from memory for the word, the state, it will calculate the hash, and then it will write the resulting state to memory. So after this lookup is done, in the next step, the CPU will have the result available. Okay, and now this is the final part, and it's about benchmarks. And I added a big warning, because I think Yingtong already mentioned before in the context of lookups, but here it also applies. Benchmarks are tricky. There are many subtleties. So some projects may have CPU implementations, others may have GPU implementations. Some projects may have better parallelism right now and others worse. Some projects support continuations and recursions and the other don't, and this can affect the performance of a single chunk of proof. And also different projects are at different stages of optimization. So, I mean, the results could change next week or in a month. So here are the results presented from the Jolt authors. So these are the last results that I think have been done in terms of zkVMs. And it compares three projects, Jolt, SP1, and RISC-V. And currently, so this is, for SP1, this number in parentheses is the number of segments. So segments are very easy to parallelize. So if there are many cores and computing a single segment is not fully parallel, when you do more segments in parallel, of course you get better performance. But as you can see, I think, well, the main take of this for me is that they are all in the same order of magnitude. Probably, I mean, RISC-V now seems to be the slowest, but maybe in a month they come up with an optimization and they get back. Also, RISC-V is the more feature complete. So they have continuations, they have recursion, whereas SP1 doesn't, and Jolt doesn't have continuations, doesn't have coprocessors. So it's possible that once they add these things, they are more comparable with RISC-V. But another way to take a look at these results is these numbers also provided by the Jolt authors, which is that currently Jolt can prove 100K instructions per second. So this would be like if you have a CPU that is computing 100 instructions per second, you could be able to generate proofs in real time. And this can give a nice idea of where are we now. And probably this number will increase. And as a comparison with real cases, this proving speed would be 2 times the Apollo 11 mission or 30 times lower than a TI-84 graphical calculator. So that's my talk. This is a QR with the slides, because there were a lot of footnotes and I was not able to, I didn't have enough time to go through all of them, but you can scan it and get the slides. Any question?
Thank you, Edu. It was very interesting. I'm curious about when you talked about segments for SP1. What's the trade-off here? Can you add like as many segments as you want, or what kind of impact does it have on the final proof generating process?
So in SP1, I think it's not fully implemented because they have segments and you have one proof per segment, but there's no aggregation. So the more segments you have, the final proof keeps growing linearly. So I guess the next step will be do aggregation and be able to aggregate these segments proofs. And for aggregation, probably they need to find some trade-off. But for now, so I think one of the points of high performance of FP1 is the fact that they are not doing aggregation yet. For RISC-0, they already do aggregation. So that's seen here. So they already account for these trade-offs.
Any question, comment? Yes, one question about the slide. So you have said that you can prove the segments independently, but anyways, the execution of these segments is not independent of each other, because the input of the, let's say, the subsequent segment is exactly the output of the previous one. And the ordering is also important. So one thing that I do not clearly see is why can you prove independently things that are not, in essence, independent?
So it's the proof that is done independently, but not the execution. So you do the execution trace linearly, and then when you get the whole execution trace, you split it, and then you could send this to different servers, and each one computes the proof.
Yeah, but it's like you have to prove that at least you have to prove the ordering, because otherwise I could take a segment and substitute the segment for another one that I'm interested on, or something like that.
What ordering?
So I don't know. For example, I take the third segment. Let's say I'm a malicious prover. I take the third segment, and I substitute this segment for another one that is different from the first one, or I can swap two segments and anyways prove this execution, which is completely different from the.
So I don't know the details, but I assume that in the aggregation step you're connecting inputs and outputs from segments, and they include at least the Merkle roots that contain the memory, but also the state, which is the registers. So if you swap them, that will not match, and the aggregation will fail.
Okay.
Any other question?
Yeah, I think that they are just doing openings of the Merkle tree and just checking the value is the correct one. So I think they're spending the half of the proving time only for openings in the Merkle tree of the memory.
Yeah. So inside the segment, they do the reordering of all the memory operations, but between segments, they fully commit the memory to Merkle trees.
So you're chaining
Any other thing? Well, if not, thank you again.